Assalamualaikum, hello everyone. We are from Group 2 and today we'll be explaining on Chapter 7, Dimensional Analysis. Let's go. In this chapter, there are 4 subtopics: 7.1 Dimensions and Units, 7.2 Dimensional Homogeneity, 7.3 Dimensional Analysis and Similarity, and lastly 7.4 The Method of Repeating Variables and the Buckingham Pi Theorem. A little intro on the chapter. In engineering, the application of fluid mechanics in designs make much of the use of empirical results from a lot of experiments. This data is often difficult to present in a readable form. Even from graphs, it may be difficult to interpret. Dimensional analysis provides a strategy for choosing relevant data and how it should be presented. This is a useful technique in all experimentally based areas of engineering. If it is possible to identify the factors involved in a physical situation, dimensional analysis can form a relationship between them. The resulting expressions may not at first sight appear rigorous, but these qualitative results converted to quantitative forms can be used to obtain any unknown factors from experimental analysis. By the end of the chapter, you should be able to develop a better understanding of dimensions, units, and dimensional homogeneity of equations. Understand the numerous benefits of dimensional analysis. Know how to use the method of repeating variables to identify the non-dimensional parameters. Understand the concept of dynamic similarity and how to apply it to experimental modeling. Now, 7.1 Dimensions and Units. Dimension is a measure of a physical quantity without numerical values. Unit is a way to assign a number to that dimension. There are 7 primary dimensions: mass, length, time, temperature, electric current, amount of light, and amount of matter. As for non-primary dimensions, they can be combinations of the 7 primary dimensions. For example, length is a dimension, but centimeter is a unit. You can refer to this table for the symbols for each dimensions: mass M, length capital L, time T, temperature capital T, electric current capital I, amount of light capital C, amount of matter capital N. For example, pressure equals to force over area. We know that force equals to mass times acceleration and area equals to base times height. If you write it in dimension form, mass M, acceleration L over T squared, area L squared, and finally you'll get M over LT squared. This is dimension for pressure. Next, 7.2 Dimensional Homogeneity. The law of dimensional homogeneity. Every additive term in an equation must have the same dimensions. Simply said, both sides, left-hand side and right-hand side, must be equal terms. For example, let's take our favorite Bernoulli equation, P1 over rho g plus V1 squared over 2g plus Z1 equals to P2 over rho g plus V2 squared over 2g plus Z2. If you take the first term, P1 over rho g, if you write it in dimension form, you'll get L. For the second term, V squared over 2g, you also get L. And lastly, Z, you'll get L. So if you substitute this, you'll get L plus L plus L equals to L plus L plus L, which means that it is homogeneous.
Hi, I am Husna and we continue presentation on topic dimensional analysis and similarity. In most experiments, to save time and money, tests are performed on a geometrically scaled model rather than the full-scale prototype, which is the real product. In such cases, the general analysis must be done to properly scale the results. Here, there are 3 primary purposes of dimensional analysis, which is the first is to generate non-dimensional parameters that help in the design of experiments, either physical or numericals, and in the reporting of experimental results. Other than that, to obtain scaling laws so that the prototype performance can be predicted from model performance. Dimensional analysis also needed in order to predict trends in the relationship between parameters. Okay, next we move to the principle of similarity. There are 3 necessary conditions for complete similarity between a model and prototype. The first one is geometric similarity. Model and prototype have same shape. In geometric similarity, the linear dimensions on model and prototype correspond within the same scale factor. To be clear, in aspect length, breadth, depth, diameter, area, volume, both for model and prototype must be same. For kinematic similarity, its mean velocities at the corresponding points on model and prototype differ only by a constant scale factor. So in aspect velocity and acceleration, both for model and prototype must be same. In dynamic similarity, force on model and prototype differ only by a constant scale factor. Dynamic similarity will achieve only when all forces in the model flow scale by a constant factor to corresponding force in the prototype flow. As for example below, the direction force for model and prototype is same. In a general field, complete similarity between a model and prototype is achieved only when there is geometric, kinematic, and dynamic similarity. To ensure complete similarity, the model and prototype must be geometrically similar, and all independent groups must match between model and prototype. The similarity equation. So the conditional statement for achieving similarity where pi denotes then dimensional parameter, which is pi pi model equal to pi prototype. Thus, we can write Reynolds number model equal to Reynolds number prototype. The Reynolds number is formed by the ratio of the density, characteristic peak, and the characteristic length to viscosity. Alternatively, it is the ratio of characteristic peak and length to kinematic viscosity. The Reynolds numbers is the most well-known and useful dimensionless parameter in all of fluid mechanics, especially to prove dynamic similarity. The other equation to achieve similarity is shown below. Remember, if the two fluids do not have the same properties, the two drag forces are not necessarily the same even under dynamically similar condition. But similarity can be achieved even when the model fluid is different than the prototype fluid.
The Buckingham pi theorem was named after the American Edgar Buckingham. It states that if there are n-dimensional variables in a dimensionally homogeneous equation, described by j fundamental dimensions, they may be grouped in k equals n minus j dimensionless groups. Each dimensionless group is called pi. And the relation among the dimensionless groups will be written as follows. Function of pi 1, pi 2, pi 3, until pi k equals 0. Or pi 1 is a function of pi 2, pi 3, until pi k. Or pi 2 is a function of pi 1, pi 3, until pi k. And so on and so forth. All these presentations are similar. This method is also known as method of repeating variables.
Next, this is subtopic 7.4. The method of repeating variables and the Buckingham pi theorem. It is a method to generate the non-dimensional parameters. There are several methods that have been developed for this purpose, but the most popular and the simplest one is the method of repeating variables. However, this method cannot predict the exact mathematical form of the equation. This method has 6 steps. I'm going to explain these 6 steps. Step 1. We have to list all the parameters, including dimensional variables, non-dimensional variables, and dimensional constants. We have to let n to be the total numbers of parameters in the problem, including the dependent variable. We have to make sure that any listed independent parameters is indeed independent with each other. For example, we don't include radius r and area a since they are not independent. Step 2. We are going to list the primary dimensions for each of the n parameters. For example, velocity will be L power 1 t power negative 1, and the gravity acceleration will be L power 1 t power negative 2. Step 3. We have to guess the reduction j. First, set j equal to the number of primary dimensions represented in the problems. According to the Buckingham pi theorem, k will be equal to n minus j, where k is the expected number of pi. If at this step or during any subsequent step, the analysis does not work out, we have to verify that we have included enough parameters in step 1, otherwise, go back and reduce the j by 1 and try again. Step 4. We have to choose j numbers of repeating parameters that will be used to construct each pi. For example, if our j is 2, so we have to choose 2 repeating parameters. Since the repeating parameters have the potential to appear in each pi, we have to be sure to choose them wisely. Then we have to refer the guidelines in table 7.3. A little hint, a wise choice of repeating parameters for most fully closed problems is length, velocity, mass, or density. These are the guidelines in table 7.3. As you can see, for example, the first one, never pick the dependent variable. The second one, the chosen repeating parameters must not by themselves be able to form a dimensionless group. And the third one, the chosen repeating parameters must represent all the primary dimensions in the problem, and so on. So every time we want to choose the repeating parameters, we have to refer to these guidelines. Next step, step 5. We have to combine these repeating parameters into products with each of the remaining parameters, one at a time to create the pie. The first pie is always the dependent pie and is stored with the dependent variable. In this way, we will construct all k pies. Then, we have to let the products to be dimensionless. Sometimes, we have to manipulate the pies as necessary to achieve the established dimensionless group as stated in table 7.5. Last step, which is the step 6. We have to check all the pies are indeed dimensionless. Then, we will write the final functional relationship in the form of pi1 equal to function of pi2, pi3 until pi k. That's all.
My name is Leong Kei Xiong. Now I will be explaining a sample problem from this topic, which is problem 7-52. Given the question as shown in the slide, consider a fully developed contact flow, which is the flow between two infinite plates separated by a distance h, with the top plate moving and the bottom plate stationary as shown in the figure. The flow is steady, incompressible, and two-dimensional in the xy plane. Use the method of repeating variable to generate a dimensionless relationship for the x component of fluid velocity u as a function of fluid viscosity mu, top plate speed v, distance h, fluid density rho, and the distance y. And next, we will be figuring out the solution for this problem. As mentioned in the question, the step-by-step method of repeating variable is applied to obtain the non-dimensional parameters, which is all the pi's. For this method, there are a total of 6 steps needed for us to solve this question. Step 1, we need to identify the number of parameters n. From the question given above, we know that there are 6 parameters, which is u, mu, v, h, v, and rho mentioned in the question. So the n will be equals to 6. Next, we need to list out all the primary dimensions for each parameters. For u, which is L to the power of 1, t to the power of -1, which is the same as v. For mu, the primary dimension is m to the power of 1, L to the power of -1, and t to the power of -1. For h and y, both the primary dimension are the same, which is L to the power of 1, and at last, for rho, the primary dimension is m to the power of 1 and L to the power of -3. Next, we need to set the number of primary dimensions as j, as we need to find the expected number of pi's in this question, given the formula k equals to n minus j. From step 2, we know that there are a total of 3 primary dimensions, which is m, l, and t. Therefore, our j will be equals to 3 and the number of expected pi will be equals to 3 by using 6 minus 3. Next, we need to choose the j repeating parameters, which is 3 repeating parameters for this question. So, the repeating parameters that we choose is v, h, and rho. And why we are not going to choose mu and y as the repeating parameters? If following the guidelines outline given in table 7-3 in the textbook, we are not going to pick both of these parameters as it is undesirable. It's better for us to pick a fixed length h instead of a variable y. Otherwise, y would appear in all the pi's, which is undesirable for our solution. For step 5, we need to construct all the pi's. Since for this problem we have a total of 3 pi's, and we need to construct all the pi 1, pi 2, and pi 3. For pi 1, which is equals to u v to the power of a1, rho to the power of b1, and h to the power of c1. And the primary dimension for the equation of pi 1 is shown in the slide. Next, by using the comparison method, we can find out all the value for the unknown. After we figuring out all the value for the unknown, we need to substitute back into our primary dimension equation of pi 1. And at last, we get that our pi 1 is equals to u over v. For pi 2, we construct it as mu v to the power of a2, rho to the power of b2, and h to the power of c2. By using the same method, we need to construct the equation of primary dimension for pi 2. And by using comparison method of both pi 2 equation, we get to know all the value of unknown, and we substitute back into the equation, and at last we get that pi 2 equals to mu over v rho h, which is the inverse of Reynolds number. So we can modify this pi 2 into v rho h over mu, and at last we get that pi 2 equals to Reynolds number. For pi 3, we construct it as yv to the power of a3, rho to the power of b3, and h to the power of c3. Using the same method as pi 1 and pi 2, we get to figure out all the unknown value of the primary dimension equation of pi 3. And at last, we get that pi 3 equals to y over h. For the last step, we need to write all the final function relationship of the 3 pi. Thus, we get that the relationship between the pi's is u over v equals to the function of Reynolds number and y over h. In conclusion, all the pi's are indeed dimensionless in this question. That's all for our presentation by Group 2. Thank you for listening and thank you for your attention.